Anything else? All right, cool. So a sheaf is, as we said, a data structure. It pairs a domain of validity in some sense, which will get a little more precise answer. And that actually answers the question about why commutativity that you were asking about path independence. Did you remember you had asked that question? So that will explain why. And it pairs that information with data, these stocks, the sets of possible values that are localized there, along with how the model changes when you move from one domain of validity to another. In fact, the reason why they're called restrictions is because they go from a bigger to a smaller one. We'll see that in a moment. So that is a restriction. It's a function in PySheaf. It is code, like an actual function. So you can put in whatever you want, literally. That means if you don't like numeric data, you want categorical data. We've shown most of our examples are numeric. If you want categorical data, that's fine. I even have a student, actually now graduated, now colleague, that is using with the values are graphs, nodes in a graph. That's fine. Optimizers don't like graphs. Challenge, we need different optimizers. That's why we want the pluggable interface for that. Okay, so an assignment is some data that's in the sheaf, and consistency radius is like a generalization and aggregation of statistical residuals. Okay, so let's be a little more precise about what this means. So I said we start out with a partial order, and we're going to think of this partial order as a category. So each node in our Hasse diagram for this partial order is an object. Each order relation is an arrow, a morphism. And if you realize your partial order as a category, the thing that you will notice is there is no more than one arrow between each pairs. That's what makes it a partial order category. As such, if I go from here to here, or I go from here to here to here, I get exactly one path. This means that there's only one way to get from here to here, even though it looks like I can go take a detour. In the category, when I go from here to here to do composition, I've got exactly one path. This is why path independence is because we're dealing with a partial order category space. It cannot be any other way. If I generate a category from this partial order, this is what you get. Now, what does this mean? I mentioned topology. We want to think of predictions. The arrows are telling you how to get from here to here, how to predict what happens when I move from one place to another. We saw in the least squares regression, as well as in the fox hunting example, as well as in the Titan example. I had a locus of data here that was somehow hidden from us, some latent variables, and then some observed variables higher up. And the arrows were predictors. They were functions that predicted values. In a sense, as you move up, you're doing more and more predictions. Where is this data valid? It's valid everywhere downstream or upstream in this picture, everywhere following the arrows. So the domain of validity is an upwardly closed set. That forms an open set in the Alexandrov topology built from this partial order. So when we talk about open sets, you might think of open sets in Euclidean space, the real line. There are these uncountably infinite things. Here, they're actually finite. Open sets here are finite. They're just everyone that's upwardly closed. Well, okay, there are lots of open sets in this picture. Here's another. And in fact, you will notice the intersection of two upwardly closed sets, which is the intersection of the shaded region, is also upwardly closed. It's closed under intersection. It's not closed under union. So we just assert that those are open to. Now you have something which satisfies the axioms of a topology. So the point is, domains of validity in our modeling discipline that we're building are these open sets. And in fact, what we're building, if you want to get technical about it, a sheaf is a special kind of functor. Just any old functor is a pre-sheaf. A sheaf is one in which whenever we take these unions and we look at that open set, it does something reasonable. It doesn't go haywire. The data that are there are somehow fully consistent. Let's quantify that idea. So in order to do that, we need to put some data on each of these elements. They generate the open sets. These are the stocks. They could be anything that you want in a data category. For our purposes today, they're all going to be numeric, but they don't have to be. So here I've dropped down multiple copies of the real line. So R2, vectors of length 2, R3, vectors of length 3. And just for concreteness, I need to lay down functions on the edges. just for concreteness, I'll make them linear. They don't have to be linear because in PySheaf, they're code. No requirement that be linear. Okay, and so there, if I go from here to here, it's a matrix that goes from 2 dimensions to 2 dimensions. Hey, that's a 2 by 2 matrix. So this 2 by 2 matrix lives on this edge. How do I get from here? I grab a vector, column vector of length 2, multiply it by this 2 by 2 matrix, get a new column vector there. If I go from here to here, 2 dimensions to 3, hey, that's a 3 by 2 matrix, and so on. The path independence that Donna mentioned, that's a requirement that each triangle in this diagram commutes. Path independent. And that's a consequence of the fact that we want this to be a functor. So when you say functor, beware. I know everyone likes to say, hey, we're building functors, right? Awesome. Beware, there are axioms you need to satisfy. If you don't satisfy the axioms of a functor here, you will not get commutativity. Now, as Donna also pointed out, you can kind of violate this because there's some noise tolerance. We'll see that. But theoretically, it better commute. So what do I mean by that? If I go from here to here to here, matrix multiplication is matrix composition. Hey, check it out. Matrix multiplication of those 2 associated matrices is, hey, look, the matrix was there. And this happens everywhere on the diagram. Lots to check. Good exercise if you feel that you need a little practice multiplying matrices. Okay, so what's an assignment? An assignment is a value picked out of each of the various sets. You can have a global assignment, one picked out from every, but you can also have a local assignment, just picked out of some of them. And furthermore, in PySheaf, we tag some of them as optimization cells and some of them as not. Either saying, this is an observation I trust, I measured it with my own equipment, it ain't changing, versus those that are optimization cells where I say, this is a latent variable, please estimate what it is. You get to make that choice. That sets whether it's a forward problem, an inverse problem, or something in between. Okay, so that's an assignment. What if it's consistent? As in, if I take this value, multiply by this matrix, hey, I get that value. Take that value, multiply by, I get that value, and so on. All the way, every which way that's possible, you get what is called a global section. You could think of this as a fully coherent state. Intuitively, a fully coherent state of the system is like a data that is fully predicted and consistent with the model that's described by the sheaf. All right, seems reasonable. How many global sections are there? Lots. If I have a sheaf of vector spaces, the space of global sections is itself a vector space. If we're dealing with metric spaces, as PySheaf does, the space of global sections is a metric space. Cool. Now, what if it's not consistent? Like real world is messy. What if I switch this -1 to a +1? It's no longer consistent. Okay, still an assignment, not a global section. Because if I do this matrix multiplication, I don't get +1, I get -1. Some amount of error. That error is localized to just that part of the diagram. Up top, there's no error. This is what I mean by the extent of the coherence of the state. You can ask, what is the largest open set that's fully consistent? What is the smallest open set that is fully consistent? Are there any? To what level are they consistent? These are all questions that you can now ask. If you think, now to be rather concrete about this, I have a system that I've written down and I trust some part of the model and I don't trust some other part of the model. This gives you a concrete, unambiguous way to tell whether or not you're right. And furthermore, you can measure it. So you can look at the residuals that show up. What's the residual along this arrow? I tried to predict a -1 got a +1. How much error is that? I tried to predict here, got some more error. Tried to predict some more error there. All of these are residuals. The aggregate of these residuals is the consistency radius. Now, there's some ambiguity when I say the aggregate, because it's not the aggregate. There are multiple aggregates. Lots of them. Which one should you pick? Guess what? It's a design question. That's what the norm type is. If you want to aggregate them by least squares, that's L2. You put in norm type 2. If you want the max error because you're really intolerant, that's the default setting. You want some sparsity, put in L1. Something in between, well, something in between. This is a design constraint. In fact, actually, general theme with PySheaf, If you don't like using Euclidean space, that's pluggable too. You could swap it out for your own metric. Want cosine distance? You can have it. Want something else? You can have it.
Brief comment. I don't think IIT 4.0 has an explicit mechanism like this, but and also, you guys haven't heard anything about IIT 4, so, tomorrow you'll hear. But this is probably highly relevant, right, in terms of relation and the consistency and, the extent of the, kind of border of consciousness, actually, I think. But we'll come back to it.
Cool. Cool.
With this partial consistency, are we still in the neighborhood of a full sheaf, or are we talking about a pre-sheaf?
No, this is the assignment within an actual sheaf.
With the actual sheaf. Okay.
This is we have the diagram. The sheaf does not have these values. It has sets here.
I see.
Yeah. Right. So this is the sheaf. We have not changed this. We've now selected values.
I see.
Right. This is an important distinction. And it took me a long time to come to this distinction that, no, we build a sheaf. Do not build pre-sheafs. Build the sheaf. Okay. But then slot your data in. Let your inconsistency happen in the data.
Oh, interesting.
Let your inconsistency happen in the data. You may get fully consistent data. You may not. Now, interestingly enough, if you don't want to do it that way, and you say, I want maybe a different sheaf, the consistency radius is a continuous function of both the assignments and the restriction maps. But it's a weird topology. It's compact open topology, if you know what that is. All right. Cool. So, I just said that. Right. So the consistency radius is a continuous function of the assignment, which means vary these guys by a little bit. The consistency radius changes a little bit. But it's also vary these matrices a little bit, varies a little bit too. Proof is a bunch of inequalities. It looks like numerical analysis. Anyone here like numerical analysis? Actually, I don't, but I did the proof. Anyhow, so right, let's sort of drill into this fox hunting example. So as Donna said, the interesting thing with amateur radio fox hunting is everyone brings all the equipment they have, and it's heterogeneous. Some of it is kind of sophisticated. So we have some reasonably expensive equipment with a custom antenna. Some of it's a little more portable, like Donna with a portable antenna. Some of it's got a really good directional capability. This antenna's got a very good directional antenna pattern. So you can measure different things at different levels of accuracy with different capabilities. How well can you find the fox? This is a question that's addressable. So in fact, let me sort of drill this down. If you have just a little radio like this, does it send radio waves in all directions? Yeah, right? But if you hold it close to your body is made out of what? You're a bag of water, salt water. Salt water is conductive. Salt water blocks radio waves. That means that you get signals that way, but not so much behind you. So a strategy you can do is by turning yourself around. This is the signal level as a function of angle in blue. This is right behind you. You get a null. And so you can actually kind of say, hey, when I stop hearing the signal, it's right behind me. Or you can go ahead and build a fancier antenna and get this nice narrow antenna pattern and point it right at it. You get a strong signal saying, yep, that's where it is. Different kinds of sensors. Now, reality is different. Again, we want to be really grounded. I mean, I'm fundamentally an engineer. I like to build stuff. Test these kind of systems. This is simulated. When we actually measure it, this is the actual measured patterns. They're kind of garbage because the car is made out of what? Metal. Okay, that's okay. Why is that okay? Because, hey, guess what? I can write this as a function in Python and drop it in. We're good to go. Okay, so how do we build a sheaf? How do we do this? Well, the thing to realize, and this is something that we're going to see over and over again, is we often build things in the category theory language that are called spans. We sit down at a central point with some latent variables that we cannot observe, and we map out with known predictions to values we do observe. This is a very standard construction in category theories to build a span. So you've got some kind of object in the middle with morphisms going out. So this is a design constraint. We don't know the fox. We do know the sensor position, but we don't know the fox. So we don't know this guy in the middle. But we build out a span. The span pulls out a projection for the fox position, allows us to compare it with others. We don't know what it is, but that's fine. And we also project out, okay, we know the sensor position. And so we can predict, given that we know the Fox position, given that we know the sensor position, what would be subjunctive, what would be the bearing. S1, for all of you non-topologists, is the circle, angles. So we're predicting angles from a known position of the Fox, known position of the sensor. Of course, the fact is we don't know the Fox. That's okay. Because what are we going to do? We're going to tag that guy up there and say, hey, that's a cell we're not going to optimize because we know that value. And these guys over here are cells we are going to optimize. Now, if we just have one angle, can't find the Fox, right? Because we just get a single bearing. So let's add another one. Let's put two spans, one on either side, put the Fox in the middle. Now, if we look for global sections, you will notice they have to be coherent across everything, which means that the Fox position has to be the same for both sensors. If the Fox position is the same for both sensors, then we actually get an intersection of sight lines, which of course you'd say, dude, I could have intersected sight lines without sheaves. But if I start throwing in other sensor types, you're actually kind of out of luck. This methodology is the only methodology that will actually work. Let's try it out, just intersecting sight lines just for a moment. So if I place a sensor here and another sensor there, and they receive values that I'm showing by the arrows, so those are the angles they're receiving, and I say, what are all the possible consistency radii I would get if I put the Fox at each of these X and Y values, you will notice, hey, we get a consistency radius of 0 right smack dab in the middle, the intersection of the sight lines. It works. For this case here, Donna had mentioned, how far can you get away and still get the thing to converge? Here you get as far as you like, because there's a single global minimum and no local minima. So the optimizer is just going to work. It can't fail. But of course, you can have other situations. What if I have two sensors and they read out values that are inconsistent? Where's the intersection of those sight lines? Doesn't exist, right? There is no global or even local minimum. The optimizer will fail to converge. And just as Donna said, consistency radius will not go down to 0. That's your sign. This is a problem. So you can infer that this situation is somehow inconsistent with, the data we've collected is somehow inconsistent with the sheaf model we've posited. Very much thinking along the lines of the Judea-Pearl mindset of building cause and effect structures, causal models. The sheaf is your hypothesis. The data is then your observations that you'd like to test whether they fit your hypothesis. Okay, but the great thing about this is it's composable. I could say, let me take my previous sensor that just had the bearings and splice on a few more sensors. Splice on 2 more sensors that measure, say, signal strength. So on this side is the partial order. On this side are the restrictions. So I had my original sheaf of the 2 sight lines intersecting, but now I drop in things that have signal strength. The labeling isn't so important, but recognize that this is something that if you want to do in general, in fact, I've talked to people that do things like search and rescue operations. They have to write special purpose software to do this. It's very expensive, it's very complicated. This is really easy. You can just sort of slot in more and more things. This is the real power of category theory. It's composable, it's functorial. You can do this. Make a complicated model of your neural system. I don't know what it is. Build something small. It can grow. It supports that. Great. Is it noise tolerant? I've mentioned that. It's provably noise tolerant, but is it really in practice? What if I take bearings and I noise them up? So the x-axis on both of these plots is the amount of noise I'm going to put into the system. So not very much noise, lots of noise. Not very much noise, lots of noise. This is just the bearing side of the house. This is just the signal strength side of the house. Both are involved in this particular example. The vertical axis on the top 2 plots tell you consistency radius, i.e. residual that you're seeing just given the noise before we've optimized it. You can see as you increase the noise, the consistency radius goes up. That's reasonable. Then when you run the optimizations, we can then say how much location error do I have? That's a function of noise. And that location error is brought way down. It's very effective in controlling that. And actually in the case of signal strength error, it basically stabilizes. The optimizer is very effective using this sheaf methodology at eliminating the noise. This is a nonlinear optimization technique. It's very effective. That's right. I didn't do the combined just because it's a little hard to see that intellectually, the two sources of error. Of course, it's easy to drop that into the simulation if you care. In fact, there's a link down here to another set of Jupyter notebooks that you can play with all of these constructions as well. The point is, you can build these models. They're very flexible. They're noise tolerant. They measure some notion of the extent of coherence. Okay, now this has been, amongst my colleagues, we've generally called this process artisan sheaf crafting, which is to say, I need to have someone who knows what they're doing build the model. Which, okay, great. If you're an expert in the kind of models you want to work with, fine. But that doesn't scale. So the next sort of thing we want to do is we want to start talking about more elaborate models that you can then say, all right, great, how do I use them? And so from a standpoint of, again, standpoint of what we're doing, sheaf is a data structure for modeling consistency, assigned it as an instance of the data. And this split between always use sheaves and put all of your errors in the data is really kind of practically important. Consistency radius aggregates these residuals, tells you how well the data and model fit together, and then you can optimize on that consistency radius to run all manner of predictions. Questions before we do hand over to some more computational work?
Hi.
Yes.
This is a general question, and maybe reveals my lack of understanding of the sheaves thus far. But I'm curious what benefits this approach has over something like, say, beamforming. You know, which would also be used.
I'm so happy you asked. Okay. I'm so happy you asked, because actually, in a former life, I did a lot of beamforming work. Beamforming works great when you have linear systems. This does not care if it's linear or not. If you have nonlinear beamforming, which is totally a thing, the issue is it needs homogeneous data. Here we have no requirement of homogeneous data. Now, flip side, if you do have homogeneous data and you do know it's linear, this will yield the same algorithm that you would have used with beamforming. But don't do it in PySheaf, because PySheaf has all this extra infrastructure that then consumes memory and runtime. It's the classic situation there.
Can I just follow very briefly? Yeah, I'll just say the reason I asked about beamforming, I mean, in addition to the fact that you can use it to triangulate hidden objects in general, is that it's one of the most widely used methods for solving the inverse problem with MG.
Absolutely.
As you already know. And so, yeah, definitely something to discuss further.
Absolutely. Good question.
So the way you assign each edge, the metrics you give them, can I understand more or less like a convolutional kernel or something?
You could.
And that you put all the things like whatever you given as data, and then you're using those kernel choice to find out, yeah. Okay.
Yes, absolutely. Yeah, that's a good model to have in your head. However, again, the convolutional models presuppose homogeneous data again. This we're saying the real world is heterogeneous. We really want to be able to support heterogeneous data. All of the existing methods and methodologies that people tend to use for doing signal processing presuppose homogeneous numeric data. This gets you away from that.
On this topic of heterogeneity.
Oh, yeah.
Yeah, so,
sure.
Can you elaborate a bit on how this generalizes to context-sensitive situations where you have sensors detecting all sorts of signals, but only a subset of those signals are relevant, though you still need to monitor the totality of signals?
Yes, hold that thought. Pre-thought. There's a notion where you don't want the largest open set.